Welcome, everyone. My name is Vincent Salucci. I am a program maker in the Library Learning Center. I want to welcome you to, I believe, I don't know, I think it's the 6th SHERobots Café in a series of 8. And I could have my data wrong here, so please don't quote me on that. But we have been tackling the theme of female researchers in robotics and looking at the work of female-led teams of roboticists, and some of these include actually approaching the subject of gender within the research too. Some of these do not, and the exhibition, which is over in the corner of the library, is a collaboration with the Universities of Sydney and New South Wales, and it presents 27 female researchers and female-led research teams work in primarily design, but work in robotics. And so please do check out the exhibition. The SHERobots team from Australia were up here and spent a fantastic week with us, and we kicked off the program with that. Was anyone at any of these events? Yeah, I see a few familiar faces. So my big goal for this program was to have as many live robots in the library as possible. So I'm continuing to deliver on this this promise and ideal. Today we'll be tackling robot bubbles and driving, and then basically we've extended the exhibition to female researchers in the TU who will be speaking on their expertise and their research in robotics here today. So it's more of a platform and bringing people together, which is one of the main goals of the SHERobots crew. So I'm very happy that you spend this time with us today. We'll have the agenda for the day is to have a few short talks. We'll have a small discussion session, and then we'll have some robots running around, driving around, I think, and wheeling around, and we might have a few interspersed in some of the talks as well. So without any further ado, I want to introduce our speakers. Saray Bakker is a PhD candidate in cognitive robotics at TU Delft. Her research focuses on intuitive and social motion planning for high-dimensional systems in multi-agent scenarios where the other agents are humans and or robots. And Laura Ferranti is currently an assistant professor with the Cognitive Robotics Department, Delft University of Technology. She is the head of the Reliable Robot Control Lab. Her research interests include optimization and optimal control, model predictive control, reinforcement learning, embedded optimization-based control with application in automotive, maritime transportation, flight control, and robotics in general. Sarah will begin our talks. Oh, you don't need to.
Okay, so hi, so I'm Saray. I'm indeed a PhD student in the Autonomous Multi-Robot Lab with us our professor Javier Alonso Mora. And I'm currently a second-year PhD student, and I would like to tell you today a bit about the work that we have been doing in our lab, and I'm also involved on mobile manipulators. So mobile manipulators are the system that you can see here, where we have a movable base and a robotic arm on top. So I think a challenge that we would like to tackle is to be just as intuitive as these humans, because humans can really well navigate around each other, operate very complex tasks while being basically in each other's social bubble or in each other's workspace, and they don't need a lot of communication for that. And this is something that we would like to have in robots as well. So for example, in a supermarket where also humans would be moving around, we would like to also have this intuitive motion planning around humans, but also, for example, around in multi-robot scenarios, if we would have multiple of these systems operating in a space, but they wouldn't be controlled by a central computer, but they would all basically I don't know, maybe be from a different provider or whatever, then we still would like them to operate safely, just like the humans. So a bit on detail on what is the problem that we're basically facing. So for example, let's imagine that we have two robots who both try to achieve picking this block or and the banana. And if they would both basically plan that like separately from each other, they would both come up with basically the same solution. So they would both come up with the same base position and the same arm position. And then of course you can see, like, if you would have like big bubbles around the robot being there for collision avoidance, then yeah, basically they will both try to struggle to reach that position. Maybe they will both try to reach it. Maybe one of them will reach it, but it's not very efficient. So what we want to have is non-conservative collision avoidance, basically. So we want to have a more realistic representation of the shape of the robot if we want to do these close-by interactions. But another thing that we have here is that, yeah, maybe we also should not try to reach the same base position and same arm position. So possibly we could like come up with a more social and intuitive motion planning approach, where, for example, the robot might maybe can also reach from another side of the table or a bit more to the right. So this is the problem that we're trying to tackle here. And what is also interesting, like in this case we have two robots, but of course a human is also, you could also see as another agent interacting in your environment. So for example, this other robot, you could also have a human moving around you, which you could also see as you could also be a robot with two arms, basically. So I would like to talk about 3 projects that we're working on, where I've been either involved in my first year, for example, on learning how to work on these things, but also the project that we are currently in, and I would like to show you how the demo works. So the first project is the AirLab project, which is a great example of a mobile manipulator in a supermarket environment. Then I would like to tell you a bit about the project that we're currently facing, where we are more interested also in how do we get multi-robot environments, for example, in a robot bar. And the third example is like the demo. So a bit about the AirLab project. So the idea was to really create a framework, a complete framework for having a mobile manipulator navigate in an environment like a supermarket, where also humans could do some shopping. And you can see here that the robot is able to avoid a collision with the human, and the only task that it's given is navigate to the Coca-Cola, because, for example, an online customer has ordered that it wants a Coca-Cola, and the robot will pick that for you. And then what they did is really also look at the complete framework. So I just talked about like base positioning, but also what's important is if you want to pick, for example, brownies or cola, and someone moves it, you still want to be able to pick the correct product. So you cannot just hard code like, okay, I will always go here, because yeah, maybe your product is different, or maybe it's moved, or a human just moves it around to just mess with you. So you'd still like to be able to achieve that. And the last part is also on the motion planning side. So if you have picked the obstacle or the object, you want to like to place it in a basket. And you can see already like these movements. We have a robot with 7 joints, so 7 like rotational parts. And yeah, you can see that even if we disturb the robot, it's still, we would like to have a movement towards the goal, but we also don't want it to be unsafe around humans. So these are all challenges that are tackled in this project by my mostly fellow PhD students. And I think they did a great job. And I would like to, for the project that we're now currently trying, is we would like to use this knowledge on navigating like around humans, and we would like to also do that with multiple robots, because then you have, again, multiple challenges that you face again. So for the multi-agent motion planning, I did a project together with Lucia on how to navigate around, have multiple robots navigate around each other. And what we did is a simulation here. So you can see we have multiple robots trying to really pick blocks very close by. And we see that, yeah, we're able to avoid collisions, which is very nice, because the reasoning behind it is that even without a high-level task planner that says like, oh, you can go there, maybe you can do like these humans in the kitchen, you can do tasks very close by together, as long as you are not that conservative about where you are and where the other robot is. And what also is an important aspect in this one is that we use forward predictions. So we can look into the future on what the other robots might possibly do and what we are going to do, and then we can also detect, like, oh, are we, for example, going to be in what's called a deadlock, which is basically as both robots try to achieve, like, usually almost similar pose or a similar goal position, and they both like try to reach that, but they won't achieve it. And then we can detect that and resolve that. So that's, I think, a nice result. Then for a robot bar, another project that I'm currently working on is more about how do we get complex tasks to work. So for example, like if you would like to run this bar and you would like to pour someone a drink or you would like to clean a table, these are not movements that are that clear to say we go from A to B. Because that's what we currently did with the block picking. We just say we go from A to B and then we grasp, basically. And here we're trying to look into how can we include learning into this. So here we see Rodrigo, who's sitting there, doing a demonstration with the robot. And you can see here that he's like, I don't know, maybe giving it 5 demonstrations on how to perform a cleaning movement to get the trash into the trash can. I think this really shows like then we learn a network, and that can from like every position of the robot in its workspace, it could find a trajectory towards the goal, so to like a path towards the goal. And this is something that is also a bit special about this method. So for example, if you would train a normal neural network, then you could also have, for example, positions in a network where it maybe go unstable. But in this network, you at least always converge to the goal, and you try to follow the motion profile that you encoded by giving the demonstrations. So what we're currently trying is we also do these demonstrations, and we can also train like a robot going towards this goal position. But what is encoded in this network is just the end tip of the robot, so this part, how that should move, and then the position and also how it should be rotated. But what we don't really have in this method yet, which could be improved, is, for example, how do we get nice obstacle avoidance with the whole body of the robot, and especially you can see with the mobile manipulator, that might be quite an important thing for our robot bar. And therefore we are now using the motion planner that we also used in the previous project, to make sure that we can have a combination where we can still track the desired motion that you encoded, like cleaning or whatever. And here still I go to goal a bit, but I'm working on it. So and then still have obstacle avoidance and also avoid, for example, limits of your robot, because you don't want to turn one joint more than 180 degrees, for example. Then the last part I would like to tell you a bit about, like, what if you are not able to avoid a collision with an object, or maybe a robot is not really in a nice position and you want a human to just drag it around. And this is a project that a master student Jelmer did, and I think he did a great job, where you can just drag the robot around and it will try to follow you and still try to keep a certain like base position of the robot. And you can see here that this could be very useful for environments shared with humans. And you can see here, for example, you can try that then a bit. You can see that like it will try to return to its base position, but it won't like try to be that stiff. And we can also, for example, follow a reference. So now I put the base movement off, and we can try it later in the demo. And you can also see that if you, for example, would encode that the robot has delivered your drink, but someone is in the way and wants to push it away, then it can still afterwards follow the trajectory or the path that you gave it. So yeah, I think I talked now about the 3 projects that I think are very interesting that we're working on or have previously worked on in the lab. I think there is still a lot to be done on multi-robot experiments in the real world, and also experiments shared with humans, because I think it's very good to get some feedback on how people actually feel when they, for example, also interact in an environment shared with these robots. That's it. I would like to also say hello to all my colleagues. If you, for example, are a master student sitting here and you would be interested in a thesis project in these directions, feel free to check out our website or reach out to me or whoever. I also would like to tell that we also do other projects on mobile manipulators. So we also, for example, have people working on drones and ground robots, and even more simulated projects, for example. So yeah, thanks. There you go.
So, hi everyone. Good to see so many people here today. So I'm Laura Ferranti, and in this presentation I want to tell you a little bit about our research towards reliable mobile robotics. So as Vincent mentioned at the beginning, I'm the coordinator of the Reliable Robot Control Lab, and in this presentation I want to present you a little bit of our mission and what is the vision of the lab. So the idea that we have is to design algorithms for the reliable and safe navigation of autonomous robots in complex environments. We work with a variety of applications, mostly in the mobile robotics domain. You can see a few examples here, and you can see these little cars also here in front, and we will have a demo later with Lorenzo. But we work also with big vehicles, boats, and autonomous drones with Dennis over there. And some of us are also looking into manipulators. But in this presentation, I will focus mostly on the work that we have with mobile robots. So the focus of our research is on the design of control and planning algorithms. So just to clarify what these algorithms are, and why they're important. So if we think of an autonomous car, these vehicles, they have sensors like, I don't know, Wi-Fi networks, cameras, LiDARs, that they use to perceive the environment. So with these sensors, they can understand where other cars are, where pedestrians are moving, for instance. And all this information can be provided to the control and planning algorithms that we are designing to then plan decisions for the actuators of these vehicles. And in the example of a car, you can think of a braking pedal or a steering wheel. So in our research, we mostly focused on complex environments. And here on the slide, you can see a couple of examples. Complex environment can be, for instance, it could be, for instance, an highway where the environment is more structured. You can have for instance, some trucks that coordinate to form what is known as a platoon. So when you have vehicles moving behind each other to maximize like the efficiency and the fuel consumption, but you can see in this kind of environment you still have other vehicles that you want to avoid. So it's still quite a challenging problem that we want to solve. We also look into more extreme cases like urban environments, if the slides allows it. So some more complex environments like a busy intersection in a city. So I don't know if this is an ideal case, but that's something that we want to solve somehow. And how can we solve this with this kind of level of complexity? So we want to look into cooperation. So when you have all these robots that can share some information. So what we think is that cooperation can be a key element to help exploit these technologies. So while with cooperation we can achieve maybe safety and efficiency, like the crazy intersection scenario that we saw in the previous video, with cooperation we also need to pay a price, because what is happening is that we are opening these robots to the outside world. So if we think of like a team of vehicles here, when they share information, then they become vulnerable to outsiders. We can think of maybe some malicious cars, like what maybe Lorenzo will show later, where we have malicious agents that try to tamper with the information that are shared among other robots. We might have faults that can compromise the cooperation among the vehicles, like a car getting stuck or unable to move. And then we can also have issues related to the privacy, because like for instance, when we try to plan trajectories ahead, we might share our future locations, and we don't want that to be known to outsiders. So we have several challenges that we need to tackle. And within our team, what we are trying to design is an approach to coordinate these vehicles by taking into account all these concerns related to safety when we navigate among humans, related to security, fault tolerance, and privacy. So that's kind of our mission. And what we have so far, so what we developed so far is an algorithm for the navigation of the robot that takes into account several aspects. For instance, we are dealing with humans, and that's mostly the work of Oscar there. I will show you some videos. When we deal with humans, we have to take into account their intentions, because it's very hard to predict how a person will move in an open world or on a street. We're also looking with Tassos over there to how to incorporate traffic rules. So we think of scenarios where at some point we will have autonomous vehicles in our cities or on the canals in Amsterdam, for instance, and there will be also vehicles that are operated by humans. So what would be the easiest way to kind of communicate with these vehicles? So we thought, okay, let's try to incorporate traffic rules, because it's something that we know how to interpret. So Tassos is looking into that. We are also looking at how to deal with uncertainties and faults. So that's mostly the work of Dennis, Lorenzo, and also Tassos again. For example, we have robots that have very complex dynamics, like these little cars that you see there, or quadrotors that fly around when there is wind and with very fast dynamics. I will show you some videos later on. And there might be faults that can occur on the robots that we need to take into account. And finally, we're also looking in how to deal with unreliable networks, like for instance, if we have delays in the network or we lose some information for packet losses. So that's what we have so far, and I want to show you some nice videos now. I mentioned that we are dealing with humans. These are some experiments that Oscar did in our new mobile robotics lab. I don't know if you were at the opening of the cognitive robotics lab, but we now have a new testing arena that is fairly nice to test our motion planning algorithms. So here in this video you can see a robot similar to this one but without the arm that is trying to cross this room, and there are people moving around. You can see on this side like a top view of the lab, and there what the robot is actually doing. So the robot sees the people, is kind of predicting where these persons are going, and is looking at possible decisions that he can take to avoid collisions with these humans. The same approach is now on board of an autonomous car that is developed in collaboration with the people in the intelligent vehicle section. It's more or less the exact same algorithm that you've seen on the little robot now on the car, and we're testing behind the mechanical engineering faculty. So from the outside, it doesn't look like much because we are not using real pedestrians yet. for safety reasons because it's still under deployment. But we are simulating some virtual pedestrians. So the car believes that there are people in front, and it's planning to avoid collisions with these virtual humans. So this is work in progress, and soon we will have more, I think, updated results on this topic. Then we have some work that Dennis is doing with the quadrotors. So here you can see Dennis with the quadrotor that he developed. And so this Dennis together with Max, that I don't see here, but so they're working on a project with the Dutch police, and we're basically looking at strategies to navigate quadrotors or also ground robots in static environments to do search and rescue operations. Here you can see a top view of our lab with 2 static obstacles, and you see what the robot is actually doing in this video. And here you can see the drone flying around. And with this strategy, so Dennis was able to run everything on this very small robot, a very complex algorithm, and is running in real time, and he can give you guarantees that the robot will not crash on the static obstacles, so these 2 pillars that you see here. Then we are also, like I mentioned, that we are doing navigation with some uncertainties, and part of the work that Lorenzo is also doing is to try to find a way to model how these robots are moving, because they're very small and there is not really a good way of finding the model. So it's using some data-driven approaches to try to kind of guess how these robots can move and how to navigate in a safe manner along a racetrack, for instance, here. So here you can see like what is the real model and what we are trying to kind of emulate with our kind of data-driven approach. We have other experiments with these little cars. Again, that's Lorenzo's work. We started testing these vehicles with communication issues. So there are some faults in the way the robots share information. And you can see that they try to coordinate and merge into a platoon formation. But at the beginning, there is some instability because the communication is not perfect, but we managed. Let me see. So after this talk and the discussion, we will also have a demo related to more the security aspect of our research, and you will see the demo here soon. I want to also thank some other people that were not directly on the slides, that they contributed a lot with this kind of research. That's all on my side. Thanks for the attention.
Thank you, Laura. And can I invite Saray up as well? Okay, I'm going to start you off with a few questions, and then I'm going to shortly hand it over to the audience, who I'm sure have better questions. But the theme of the SHERobots exhibitions, the subtitle we came up with was Ecologies of Care, and that spoke to some of the female researchers approaching sort of the complexities and interconnectedness and environments and natural habitat, with some of the themes like building, materials, and cooperation of species, these sort of things, so that research projects, and also care, thinking about how robotics, how close we are with interacting with our own bodies, which we see in some of the experiments that you showed, Sarah. So I was curious, how do you see your work or your research as an act of care?
I have to speak in this one. Okay. Yeah, difficult question. I think for me it is quite important that we make a bit of a positive impact. So I think I think these robots, like with these manipulators, they could be used, for example, also for people with a disability who would like to be more independent. For example, if you're in a wheelchair and you would have a robot pick your groceries for you, that would be very, very useful, I would say. It's not specifically this example, of course, but I do think a lot of these techniques could be used for also other applications which are more on healthcare related. I know, for example, Lucia, she works also, she's there. She also works on robotics in navigating through a hospital. Then you also have to, of course, be very careful about how you navigate safely around humans. Yeah.
Yeah, so on our side, I think we want to use robots to help humans in general. So, and we don't want to basically have the humans segregated somewhere where the robots take over the cities. For instance, I had some questions like you're using these autonomous robots for our autonomous cars. Does it mean that all the humans will be somewhere else and the cities are kind of covered by the robots? But that's not our mission. So we want to have these technologies that are helping people and simplify our lives. With autonomous cars, I think the benefits are clear. You can have you can help people with disabilities or elderly to commute from when public transport is not available in some places. So I think that there is a lot of benefit that can come from these technologies.
Okay, great, thank you. And as a follow-up to care, I was just really kind of compelled in the video that you shared, Saray, this motion profile encoding process, and you're really lifting the arm and doing the sweep of the table and everything. And does some sort of empathy or anything kind of develop there? I mean, it is really almost like a training of a pet or of anything. I don't know, a friend.
I do think we do in the lab see the robots a bit as children sometimes, because they sometimes cooperate and sometimes they do not. So I don't know. We had our Wednesday 8-hour
mostly the latter. That's
so I would say I think if you work more with them, you feel more at ease with being close by. However, of course, that could also be dangerous, because if you have a robot doing something that you don't expect, that can be problematic. And I think that's something that we try to tackle. But yeah, we see also in experiments that sometimes also, then you see the robot going somewhere you didn't expect during a test, and then you do have to press the emergency button. And in this case, we always have someone close to the emergency button. But yeah, that would of course in the future be avoided. That's needed.
Very nice. And then another maybe more serious question. Do you, for both of you, please, maybe we'll start with Laura, do you feel that gender plays a role in your research, and if so, how?
So I don't think that this kind of research has anything to do with gender. I guess it is quite inclusive in that sense. So we don't do anything that I think it has a really gender-specific drive. So
maybe it's a very practical one where you're talking about the co-agents and the cooperation. Are there different maybe profiles that would anticipate movements based on gender or something like this, or is something like that accounted for? Because we know that sort of the design problem of crash test dummies to the male anatomy or something, but is there actually any data that would say, okay, well maybe there is some different movements to cooperate with?
For our research at the moment, we simplify a lot the behavior of the humans, so that's that's not really part of what we are looking at. But I know that from like the computer vision side, when there is research to understand the behavior of humans, they try to collect as many data as possible and try to make it as inclusive as possible. Like on our side, we tested these algorithms in the lab where you have people walking around the robot with different people, so there were women or men walking around. We also tried with a person who visited our lab on a wheelchair, and it worked. So, but still, it's something that you need to account in the design phase, so to have some safety margins that accommodate all the people. So, yeah.
And how about you, Sarah?
Yeah, I think I quite agree with that. I think in most motion planning, go to from A to B algorithms, I would not see why that it would be yes or no, or whether it would not be inclusive. Yeah, but of course there's a lot of deep learned networks that you of course don't really know what is learned on. So if that would be fed with a lot of data from I mean, it could not even be men or women, but maybe also just people from living in the US or people living in the Netherlands, that could of course cause a bias that you, for example, don't detect a human if it looks a bit differently. But yeah, that's a bit on the computer vision side, I would say. In my personal experiments, I have not encountered a problem like that. I think maybe that's also more in the human-robot interaction, also maybe how people react on it. But then there's also still a big difference between people knowing the robots, which is sometimes it's very easy to do tests with people in the lab, of course, that you know and that know how our robots kind of work, than people who have no clue. And that's maybe also not man, women, but also maybe people not using these kind of technologies, maybe.
Great, thank you both. Anyone from the audience? Who wants to break the ice? Any questions?
Hi, thank you both for very interesting talks. I have a question for Laura. When you're training the robots for, say, driving-focused activities or developing the code or the algorithms, are you learning from things like actual traffic patterns from road use? Thinking of, it seems that people behave and drive electric cars differently than they do combustion engine cars, for example. So are you able to adjust your modeling based on different behaviors around like a future autonomous vehicle? Thanks.
Thanks for the question. So it's quite interesting. So most of the algorithms that we are using they come from like a question of motion. So there are some laws that you can use and to model how the vehicles are moving. Some of the research of Lorenzo, for instance, is based on data. So you need to collect a lot of data based on a driving style, for instance, or for a specific kind of robot to be able to use it in that sense. But yeah, we didn't try, for instance, for a different type of motors, so just electric cars for now. But I guess for the kind of speed that we consider what we have now is good enough. So because we look into mostly urban driving, so low speed and the dynamics that we use that comes from like Newton laws are good enough.
I need the robot moderator to roll around here.
Hi, thank you very much. Very interesting stuff as usual. I have a question about, I guess, about regulation and about liability. So how does it work? So for example, just something very simple. If you want to sell an airplane, if you want to build an airplane and sell it, you have to, and you have to do a calculation of the stresses in the airplane, say, and whether it's safe or not. You have to go through a lot of work to convince, say, EASA, that it's cool, we can fly this thing around, you can trust us. You know, how is that going to work with, if we have robots more and more autonomously operating with people? How does that map out?
Should I?
Well, both of you.
Okay.
Yeah.
So from my experience, for instance, during my PhD, I was involved in a project with Airbus, and we were trying to use these kind of algorithms that relies on numerical optimization, and they really needed the certifications. So that was something that I investigated, how to give some exact numbers of convergence to Airbus to try to implement these techniques on a real plane. But for, I think, robots like these ones that move around people, there is still, there aren't a lot of regulations, unfortunately, yet. But for instance, I attended some talks from insurance companies to kind of came up with some liability plan for when you will have autonomous cars in cities. And yeah, it is still a bit open, the question. I know there are some companies in the US that are deploying autonomous cars in cities, and what they provide as a certification is that their cars have bumpers. They go slow, and if they bump into a person, there is some margin. But on our side, for instance, the research that Dennis is doing with the quadrotors, so we have some mathematics behind that gives you some real tangible guarantees that the things like that the drone will not crash with the environment. So as far as long as we can use some math and numbers, we are good, I guess. But it's not always possible, especially when there are humans where their kind of behavior is impossible. And if we look at the US, what they're doing is to add bumpers. Maybe we will go along that line also. It's not ideal, but that's what it is.
Yeah, I think I agree. I also think, for example, if you now go to some restaurants already in the Netherlands, you always have the robot giving you the desserts. They bring you the desserts. And that's okay, right? We are okay with this robot being there, and we don't feel very unsafe. But yeah, of course, we have to be careful that we don't cause any accidents. And I think that's always tricky, right? To where a bit like how much we think is safe, and also like humans are also not always safe. Everything we do, but of course you don't want your robot to be more unsafe than what humans do. For example, also with the driving, human drivers could also cause accidents. But yeah, I also agree. Like the autonomous driving in the US that's already employed, for me it's like, oh, okay, apparently this is already possible. I think here there would still be a long way before that's allowed. But yeah, people can already operate these systems in the real world. So.
In a situation where there are, for example, multiple agents, for example, in a search and rescue mission where multiple people could be using drones to find someone, it's quite likely that if you have multiple agents that the drones could not communicate well with each other because they're just built different. How would you see that working? That they still collaborate with, efficiently without the ability to directly communicate with each other?
Yeah, so our idea in that context was to have maybe a human operator that will kind of supervise a team of drones and send some objectives for these drones, and then they will have on board some sensing capabilities to see where other nearby vehicles are, and they will do kind of similar to what the ground robot was doing with the pedestrians. They will behave in a similar way to avoid collisions with each other. So that would be the case. But in that kind of mission, so the hope is that maybe there is some communication in place and there is at least a human on the ground that is supervising the mission, I think. But yeah, it's a challenging problem, and yeah, we don't have a good solution yet.
thank you for your presentations, and I'm really interested of one of the slides of yours, of Laura's, about the urban environment, like how to cooperate with other road users at the intersections. I'm curious about when you're modeling the decision-making process of a vehicle, are that based on the decision-making process of a human, or they have other like they can process like faster than a human, like split-second decisions?
That's a good question. Yeah. So what I'm trying to do in that case, I don't think I'm modeling the decision process of a human exactly, but at least what I'm trying to replicate there is to the behavior like what a human would do. Like when you drive a car, you don't just look in front of your car directly. You try to look a bit further ahead to see if there are upcoming vehicles and if there is an upcoming turn. So these algorithms are doing exactly that. So they try to look ahead, predict what the other humans will do, but they will do it in a much faster manner. So I think they can be more efficient. But yeah, of course, they can be wrong. So there is always some risk involved. So for some of the work we are doing with the pedestrians, for instance, is also to model what is the risk. So we can provide guarantees that there is no collision with the pedestrian up to a certain amount of risk, because it's also up to the humans in that case. So it's very hard to provide like 100% guarantees that there will be no collisions if there are like uncertainties in the behavior of the agents involved when other robots are moving around. So I don't know if this answers your question. Thanks.
Might have time for one last question if there is a burning one. Okay.
Thank you for the presentations. I don't know. I haven't thought this through too much, but I think it should apply for both. It's more a question about, like, I guess, the direction of the research a bit. So if I think about myself walking a crowd, that's more or less what a mobile robot could be doing. I don't think that I'm mapping what everybody around me is doing, but probably I'm just walking straight, sometimes avoiding someone, but not really. And the same if I have to pick some objects on the table. I mean, some person, if it's only human, some person could just go grab something, I would wait and then pick my turn. So sometimes I wonder, are we maybe overcomplicating the problem by trying to take everything into account? So you have a person that just always walks straight in the crowd, and it's not that causes so much problems to the others. A person that is more shy in certain situations, but it kind of works. So I'm wondering, is the problem only that it's a robotic agent that's doing something weird? So what are we trying to mimic? A confident person, something there in the middle? I don't know if the question even makes sense, but like, what are your thoughts?
Do you want to?
Yeah, I think that's very complex, right? Because we could have just robots going only straight over like the one that do serve with desserts in a restaurant. They go over a straight line, they wait if they see someone crossing, and then they go further. It works quite well. I think it is, like, if you want to go further than that, like if we really want to have robots be used, for example, in a supermarket where maybe some things are blocked, and yeah, we want a robot to understand what the situation is, kind of. I think that's quite important. And then, like, how to plan around it. Like, sometimes maybe just going straight is fine. But if we don't understand, like, if a robot doesn't understand that this is really a block that will never be resolved, it will just stay there forever, which is a problem. But yeah, in some scenarios that might not be bad, because maybe someone can reset it and it's fine, and you hope it will continue. Or yeah. But of course, it is true that the more the robot would be able to solve itself, the less the human operator would probably have to intervene in a lot of scenarios, you hope. But yeah, it's very complex to check which algorithms would work and which one won't, and where we are like maybe over modeling humans, how they would react. Yeah, that's of course a question, but that's also something that I think is quite interesting to look into, like how realistic is it, and what do other humans think is good behavior. Yeah.
But I also, if I may add, is that I think that the bar for a robot is much higher than a human. So that's why we need to account, like overthink maybe the behavior of a robot when we deploy them in a crowd, for instance. So that I think that's one of the main issues that we have. Like we need some. Like there is always liability in that case, so that's why you need to be really, precise when dealing with robots. So that's at least my point of view.
Well, thank you very much. Maybe humans need to aspire to the robot bars. Please join me in thanking our speakers. I don't know about you, I'm very, absolutely. I'm very eager to start to play with some of the robots. If you don't mind advancing the slide one, Saray.
Yes.
I do want to remind you that we have our penultimate robot cafe about medical robots coming up with Laura Crespo and Katie Pogency. And we should have some more robot fun in the medical and healthcare context next time, a little bit later in the early next month. And with that, we'll fire up the demos, but I also see quite a few sandwiches and fruit back there, so you're not robots, so make sure to fuel yourselves and leave full. And let's do the demos, so please. And we'll bid the asynchronous audience adieu.